Now the question is, how do we combine the trapezoid rule and the midpoint rule to make an even better rule? We're going to use what's called Simpson's rule, or we're going to talk about Simpson's rule. Okay? Recall that what we talked about earlier in this lesson, the trapezoid rule was 1/2 the left approximation plus the right approximation. It was the average of the left and right approximations. Okay? And then if you recall from when you saw it in calculus, you may have observed that depending on whether the function is always increasing or always decreasing, that'll determine which of left or right will overestimate the true value of the integral. So by taking the errors from the left and the right, which would have opposite signs, by averaging them, we're kind of eliminating part of the error. Okay? We're going to use that idea and we're going to apply it to the fact that the midpoint rule and the trapezoid rule have opposite sign errors. Okay? But since the midpoint error is half as big as the trapezoidal rule error, we have to do 2 times the midpoint rule and then add that to the trapezoid rule and divide the whole thing by 3. In other words, we have to take a weighted average of these 2 approximations. Okay, so this is our formula for Simpson's rule, and I'll explain in a moment why it says S sub 2n instead of just S sub n. I will get to that question. Okay. Remember that the midpoint rule uses a point that's in the middle. So again, if I just take my example, the midpoint rule would use, that was not okay. Let me redraw that. So the midpoint rule would use this function value here to get the rectangle. So there's one function value. The trapezoid rule would use these two. So they're not using the same function values. They're not using the same x values. So I need twice as many x values to use Simpson's rule, because I'm combining 2 different rules that use 2 different sets of x values. Okay, so let's take a moment to look at the errors for the same integral we were looking at before and the different approximations we had. So these numbers were the same as what we had before, but look at the Simpson's rule error. For this first integral that we were talking about earlier, the error is actually 0. If we looked at a different integral, in this case, integral from 1 to 2 of 1 over x squared dx, which its true value is 0.5, the Simpson's rule errors are noticeably, look how many zeros there are here in comparison to the zeros in the errors for the midpoint rule and the trapezoidal rule. Big difference. So by combining the rules in this way to make Simpson's rule, we're doing a lot better. Okay. One quick comment I want to make is, when I first learned Simpson's rule, I was told that it was a rule where instead of using trapezoids or rectangles to approximate area under a curve, you're actually doing something like this. Okay, so let's say our actual curve, let's say our curve was something like that. So the way I learned Simpson's rule originally was, what you do is you take 3 points that are close to each other in the same subinterval, and you draw a parabola that holds those 3 points, and you calculate the area under that parabola. And then you take the next 3 points, which would be these three, figure out what parabola fits them, and find the area under that parabola. That's how I first learned about Simpson's rule. And we're going to talk about that connection shortly. I just wanted to point that out now. Oops. Okay. Oh, sorry. Let me say this first. So the rules that we've been talking about are not only good for approximating integrals that we don't know how to do, they're also good for approximating integrals when we just have a table of data. Okay, and I'm going to show you an example next through this activity. Okay. This problem is about velocity. And if you recall from Calc 1, when you take a velocity function and integrate it, you're getting a distance function. Okay? So it's useful for us to integrate velocity because we want to know distance. We want to know how far a car traveled based on just measuring what's on the speedometer at certain time intervals. Okay, and what you'll notice is that the velocity is always decreasing, and it's actually always decreasing at a decreasing rate. So the speed at which the velocity function is decreasing is actually it's decreasing faster and faster. Okay. You're going to plot these points here, or I mean on your own graph paper, paying attention to scale here, of course. And then the next thing will be to get a definite integral. So you're going to have to do that somehow. Then estimate the total distance by computing L3, R3, and T3. It's already telling you that they're all underestimates. Oh, sorry, it's wrong. That's not what I meant. It's saying that it's asking you which of these three is underestimating the true distance. Then the total distance, you're going to estimate it again by M3. And then answer if it's an over or underestimate. You're going to do the same thing again for Simpson's rule. So you need the results of C and D to use Simpson's rule because, as we mentioned, the Simpson's rule is given by the formula here. And then finally, what's your best estimate of the average velocity of the car? What are the units on this quantity? Give that problem a try. Pause the video.